Okay, welcome back to part 2. So we'll begin with a brief review. So we've got our L0 hypervisor, our L1 running on top of our hypervisor running on L0. We've got our L2 running on our L1. We have loads of VM control blocks in P2M tables. The VMCB01 for the L0 to make the L1. The VMCB12 which is virtualized for the L1 to make the L2, and the VMCB02, which is actually the hardware that the L0 uses to let the L2 actually run. Same thing with the P2M tables, P2M21, P2M10, P2M20, which is the actual hardware table that the hardware uses to do the translation from the L2 physical addresses to the machine physical addresses. When L1 does a VM run, the L0, it exits to the L0 will construct or update the VMCB02 by combining the information from the VMCB12 and its own hooks that it needs to add, do a VM run. When a VMEXIT happens, then the L0 needs to figure out, is this a VMEXIT that I can handle myself? Is this a VMEXIT that I need to pass on to the L1 to just handle by itself, or is it something where I need to do something and then pass it on to the L1? Okay, so now we're going to be moving on to pitfalls. So the first pitfall here is naming. So I have tried very hard to use a consistent naming scheme, okay? But even you've probably noticed me saying weird things like, virtual, this, virtual that, whatever. It's kind of confusing. The code is written by several people over several different years, and before this sort of normalized naming scheme has kind of come in, so you just get stuff that's like all over the place, okay? So, so we have the VMCB, which is for AMD, and the VMCS, which is for Intel, and there was some attempt to merge some parts of the thing which seemed to be kind of common, and so there's bits of the code which has a reference to a VMCX, which is meant to be, VMC whatever you happen to have. So you get things like this, where you have, okay, NV VMCX, and 1 VMC XPA and 2 VMC XPA. So what is this here? Right. So obviously the VMCX is the VMCS 1, 2. The N1 VMCX is the VMCS 01, and the N2 VMCX is the VMCX 02. So basically, similarly, like within the same function inside some of the nested P2M code, you have this one function is called nhvm hap walk L1 P2M, and you have another one called nested hap walk L0 P2M. Is there a reason those are named differently? I don't really know. So basically, one of the first things that if I had more time I would be doing, be going through and trying to understand what the lay of the land is, but also then try to rename things so that there's a consistent naming scheme. But in general, basically, when you're somewhere in the code, you kind of need to think about the overhead map. Okay, where are we? What are we trying to do? And make your best guess as to what some of these different things mean. Another pitfall, kind of more important, is what we call new feature leakage. Okay, so before 2020, so it's the case that if you're running in 4-level paging, CR3 needs to be page aligned. That means that the lower bits of the actual address you're using are always the lower 12 bits of the actual address you're using are always going to be 0. And so before 2020, if you were in 4-level paging mode, the lower 12 bits of the CR3 always had to be 0. This was kind of checked both in the normal HVM code and in the nested HVM code. And if somehow the VMCB12 ended up with CR3 that had stuff in the lower bits, then when you did a VM run, then the code would say that's not allowed and fail your VM run. As part of the, as one of the things to do some of the spectrum mitigation, they introduced a new feature called PCID, which I won't get into what it does, but fundamentally they said, well, look, we need some extra space for some ID bits. Hey, look, when we're running in 4-level mode, there's these 12 bits that aren't being used. let's store this PCID, this new PCID thing in those 12 bits. So after that point, if the PCID bit is present in the CPU ID, and the guest operating system has set the appropriate CR bits, whatever, to enable this, then the lower 12 bits of the CR3 are treated as a PCID. Okay. Now the normal SVM code for kind of virtual root mode was updated, but nested code was not. So the hardware now tells L0 you have PCID. The L0 tells the L1 you have PCID. The L1, which is running Zen, says, well, hey, I have PCID. I will tell the L2 that you have PCID. So the L2 says, great, I have PCID. I will set the appropriate CR bits. I will do a CR write. And the hardware says, great, you've set the appropriate, you have PCID. You set the appropriate bits. This is OK. That gets into the VMCB. And the next time you do a VM run, the L0 tries to copy stuff out of the VMCB 1.2 into the VMCB 0.2, sees these extra bits and says that's not allowed and fails the entry. At which point the L2 kills the L1 guest. Okay, so this is obviously this is a specific instance of a general problem we might call new feature leakage. Okay, so we had a similar problem with, it used to be the same problem with HVM, right? A new, we used to by default, pass all the CPU ID information from Zen into the HVM guests. So when a new hardware feature came up, the guest might try to use that, and if the L0 didn't know about that, then that could cause issues. So we started to have, we have the infrastructure now in place, such that by default, new features are not exposed to guest, unless the developer says so. And it's actually, we have the infrastructure to say, this CPU ID feature is safe to expose to HVM plus HAP, like HVM guests using HAP, or this is safe to expose to HVM guests using Shadow, or this is exposed to PV guests. And but before the CPU ID actually gets exposed to any of these things, a developer has to actually go in and say, yes, I've confirmed that this is safe. But this was not done. There's no way of doing this at the moment for HVM with nested code, right? And this is kind of what happens. And so in this case, as it happens, it was kind of safe because what happens is, the L2 guest crashes. But you can certainly imagine a case where you expose something to the L0, the L1, which is safe from the L0's point of view. But when the L1 exposes that to the L2, that opens up a bug in the nested code that allows an attack against the L0. Right? So options here, reviewers can just remember to refuse to expose new features to HVM plus HAP until they've verified what happens in the nested virt case. We can just do extensive testing where we make sure every new feature is tested both in L1 and L2. Or we can extend this functionality above to say nothing new is exposed to the nested virt guests until the developer has specifically said not only that it's okay for HVM plus HAP, but also to nested HVM guests. So obviously the first one is the easiest, but it's also the least robust. Same thing kind of with the second one. So I mean, I'm inclined to think that the third one is one of the things that we should go to for. And this whole thing, of course, is worse for Intel because all this for SVM, almost everything is exposed via CPU ID. But for Intel, there's loads of information, new features, which are exposed via MSRs. And we don't have the same level of infrastructure to do this kind of filtering for MSRs that we do for CPU ID. Yeah, and I think for each of these things, feel free to interrupt me as I'm going along. We do have some, but it's not as right. Yeah. So what I tried to say. Sorry if I misspoke, but like what I tried to say was that it's not as complete, right? So like the CPU ID stuff is like very kind of, it's fully featured. It's kind of all there. The MSR stuff isn't kind of complete yet, so there's more work to be done to make it like that. Right. So another pitfall is what we call naive VMEXIT handling. Okay. So a So you might think, so a naive way to think about of what to do when you have a VMEXIT. Suppose that you get a VMEXIT, and for an intercept that L1 has not asked to intercept, okay? What should you do with that? Now, in many cases, the right thing to do is to simply pass that on, to simply handle it in L0 as though it were a normal thing, right? So if L1 has decided not to handle, writes to this particular MSR, then essentially what the L1 has said is the L2 is allowed to write this MSR, and then the L1 should just kind of treat that as though the L1 had actually written that, right? But suppose the L1 doesn't intercept the VMM call, right? Do you want your L2 guest to be able to make essentially hypercalls all the way down directly to the L0? Probably not, no. And that's not what the hardware says. The hardware spec says if the VMM call isn't intercepted, then and the guest does a VMM call, then you will get a GP fault, right? You'll always get a VMEXIT. The only difference is whether you get a GP fault or a VMM call as a VMEXIT. So this is kind of another example. Okay, so VMM call is that one case where, okay, that's pretty clear that we actually want to do something about that. But are there other cases, right? So one of the things we need to do is to actually look through all the different VMEXITs and think, okay, if L1 weren't to intercept this, what do we actually want to do? Do we want to just pass that on to L0 and have it handle the normal way, or do we need to handle it in some sort of special case? So then just kind of moving on to future work here. So particularly for nested HVM, and probably because it's so complicated, but also in part because it is, it's intended obviously to be security kind of a boundary, right? It's not enough to kind of just say, well, this works for the happy path, right? We can't just do extensive testing and say, well, all the testing we've done in KVM, all the testing we've done for Hyper-V, all the testing we've done for Zen all works, so that's probably fine, right? Because we need to be able to defend against malicious L1s and malicious L2s. And so in a similar spirit to the kind of the FUSA stuff that we've seen yesterday, the kind of suggestion that has been made, and I think it's a good one, has been to try to basically write XTF unit tests for every aspect of the implementation. And you can imagine, they talked about yesterday, writing out the specification and then tests for all the specifications. That would be a huge amount of work. But once we had that, then that would be a really good regression test to make sure that we didn't get any regressions in the functionality. And once we had that, you could be much more confident that that this is something that we can sell onto other users and rely on for security. And the last bit of future work I want to talk about. So again, this is we're going to kind of get more and more into the kind of the hazy hypothetical stuff, right? So what we have here essentially is the P to M, right? The P to M20 is essentially a shadowed version of the P to M12. And there are a lot of parallels between, so before hardware-assisted paging existed, then the main way that we had to translate from guest physical addresses to host physical addresses was called shadow paging. Okay, so the guest would have its page tables that it used, and in the page tables it would put guest physical addresses, and the L0 had to manually create a completely separate set of page tables which shadowed the guest page tables using machine physical addresses. Okay, and so obviously the current PDM shadowing stuff, so before HAP, we actually spent a lot of time, and I was actually involved in this, and another guy named John Luca, a lot of time optimizing the shadow, the shadow paging protocol, because that was one of the major sources of hypervisor overhead. And the current P2M shadowing implementation looks a lot like the very naive, unoptimized shadow implementation for shadow page tables back in 2005. So one of the things that I'm expecting to have happen, okay, once we kind of get stuff that we're functionally sure that that it works and it's something that we can, it's not going to have bugs in it, is to look at optimizing the shadowing thing of the P2M. Now, P2Ms are different than page tables in the sense that page tables are actually changed quite quickly. And in general, I mean, unless you're doing more advanced features like playing with the page for like doing introspection or something like that, then the P2M doesn't change all that often. So it may be that the performance-wise, this is just not something that's worth optimizing. But if it turns out, like shadow paging, to be one of the major sources of overhead, then there's a lot of low-hanging fruit, and there's a lot of techniques that we can use. We can look at from the shadow code to see if they apply to the P2M code. And some of the key techniques here are that, so I'm going to describe the shadow algorithm, and we can see how that could or could not apply to the P2M algorithm. So in the case of shadow code, what you do is you promote a page to being a page table page. You remove write permission from that, and you translate the entire page from kind of the guest physical addresses into the host physical addresses, okay? When the guest writes to it, you unsync the page, okay? You allow the guest to write whatever it wants to write, leaving the shadow page out of sync with the guest page. When the guest does a TLB flush, then you find all the pages which have been unsynced, you sync them again, and you remove write protection again. So rather than having to, say, throw away the entire page tables and regenerate the whole thing from scratch, you can simply update the handful of page tables which have been changed. So one of the next things, optimizations, and again, I'm not sure this is going to be necessary for P2M or not, is that if there's a page which is already out of sync, and you get a nested page fault in the, you get a page fault in the shadow page tables with there's no entry, and you look in the guest page tables and it has been written, then you simply sync that one entry over into the shadow page tables, but you leave the guest page table unsynced, right? So we just call this sort of like a, like a lazy pull through, right? So you don't sync the whole page, you just pull through that one entry, and basically what you're doing is you're allowing the you're allowing the shadow page tables algorithm to take advantage of the promises that the TLB has, basically, so that the TLB can go out of sync, with the page tables as well. The guest already knows how to, that this happens. It already tries to avoid TLB flushes. And so basically by taking advantage of that, you can minimize the extra overhead that you have to do to keep the shadow page tables in sync with the guest page tables. So it seems like, there should be ways that we can apply the same kind of techniques to the P2M shadowing. I think I will stop there. And then we have lots of times for questions if anyone has them. Yeah, so Simon.
Yeah, so no, what I wanted to do that one of the suggestions you said was to have unit tests for execution, right?
Yeah.
Now, would you recommend a test given development or a non-given development?
Sorry, could you say the last sentence again?
Yeah, so would you recommend to have a test during development so you can use people end or more like a behavior to the development? So I will include the feature and eventually no with test.
So you're asking whether we should write tests during development or after development?
I'll take that. XTF, you write the XTF test first and then fix the hypervisor to work. That's how everything works.
That's what I would do, yeah.
What you're starting from is a simple test saying, I expect it to behave in this way. And then you find a bazillion different ways in which L1 or L2 go wonky. Those are driving development. Yeah, that certainly from the XTF unit tests, it's very much test-driven development.
Well, and I think particularly when you have, we already have a standard that's written out there, right? And we have an implementation in the hardware that we can test, and we have like KVM or something like that, right? So basically it's fairly well understood what we expect to happen. Then this kind of test-driven development where we sort of write the test, make sure it passes, write the test, make sure it passes, kind of makes a lot of sense.
The biggest problem with nested virt is put it this way. The Intel and the AMD manuals are great references if you are already a CPU designer. There is not enough information in the manuals for people who are not CPU designers to write a hypervisor. As a result, I know a lot of basis, saying, hey, how does the following thing work? Oh, let's update the documentation. Seriously, every single revision of the Intel and the AMD manuals, I've got a correction into for the past 6 years or so. Because a huge amount of it is assuming the knowledge of the people that designed the CPU in the first place. And VM entries and VMEXITs are very, very tied to the internal details. There's a whole bunch of state transitions in there that aren't actually adequately documented. And the only way you are ever going to find if you correct that is if you have a test code already.
And does this also mean that the approach of writing a formal spec and trying to prove your code correct isn't feasible?
Not until you've got a formal spec for an X86 processor, and well, good luck with that.
I think the SEL4 people might have tried.
Yeah.
I'm guessing they failed.
Marek.
Do you know some analysis of the update patterns of PTM? Because one, happen just most commonly just updating one entry or the whole page when you switch to different L to best, or and are there any patterns we can use to optimize stuff?
So there are a couple of things here that are relevant. First of all, at the moment in Zen, there's an arbitrary 10, completely arbitrary 10.
Like number of P2Ms of shadow P2Ms.
So if your L1 hypervisor has 11 P2Ms it wants to run on, you just throw away one and decide to reshadow it later. The other thing is there are a huge number of shortcuts taken whenever the host P2M changes. It just throws away all the nested P2Ms. So in particular, if you have an L1 hypervisor that's doing grant operations, I think it throws away all the P2Ms every single time it does grant unmap. So we'll need to look into that. The problem of updating nested P2Ms is so bad that one of the things that Microsoft, so in the Viridian spec, I think version 6, Microsoft have basically taken nested virt and paravirtualized it a little bit. Specifically, they have taken Intel's register layout, put it in a piece of shared memory like AMD did, so it had a fixed offset and you didn't need model-specific instructions to get to it, and provided a couple of other paravirt interfaces, one of which is, please change this one entry in that P2M and just do one TLB flush for me, not throw away the entire lot. So Microsoft found it so important to do that they actually paravirtualized it in the Hyper-V spec.
But probably what you're asking is like access, like patterns in which the L1 updates the P2M to 1, right? So for instance, when you're doing page tables, you have, it's a common thing is to have sort of a map cache where you have like, like a complete, like, a range which is completely empty, and you just map in one at a time, pull that through. So this is where the lazy pull through kind of thing works, right? So you map something, pull it through, map something, pull it through, map something, pull it through, and then once your map cache area is gone, then you flush the whole thing all at once, right? That's kind of a pattern. And there's loads of other things like this as well for the shadow code that we have discovered that the operating systems do. So, but basically, as far as this is uncharted territory, as far as I know, for what L1s do. Demi?
A couple of questions. One, could you just say that if you care about performance, use the Viridian interfaces. Otherwise, you're off to night. Otherwise, you'll get a correct but possibly extremely slow implementation. And two, would there be any use in forcing L1 to run in shadow mode and therefore avoiding L0 having to deal with nested P2M? Assuming your hardware is not vulnerable.
Well, so if you have if you're doing the nested P2M, you're exiting from the L2 to the L0, fixing out your P2M, going back to the L2. If you're running L1 in shadow mode, you have a page fault. you have to go and deliver it to the VMEXIT to the L1. The L1 has to fix stuff up, and you have to then exit back to the L0 and back to the L2, right? So that's, instead of just one back and forth, you're doing like two, right?
So it is possible to run L1 in hack mode and not advertise hacking into L1, so the L1 doesn't get hacked for L2. And yeah, that's great for Zen at L0, and there will be 0 hypervisors that tolerate it these days. So it's not really useful. It's one of the test cases we will need to test and need to ensure works, but it is not useful for making something these
Yeah.
days because everyone wants hardware paging.
Okay, does that mean that the shadow paging code in Zen can eventually just be yanked out?
You can already compile it out.
Okay.
We have it in there.
No, I mean, can it eventually be removed from the tree?
We use it for migration, as far as I know.
For PV guests. But if you're not using, if at some point we completely deprecate PV guests and whatever, could we get rid of shadow paging entirely?
I'll point out that it's file out of Zen Server 8.
Okay, the other, yeah, so what about the idea of saying that if you don't use the Viridian, we're not going to optimize the architectural interfaces. If you care about performance, use the PV ones.
So my design philosophy is get it right and then fast comes second.
Yeah. So you optimize, like, don't do early optimization, right? So like figure out what you need to be fast, like figure out what is slow and what you need to be fast, and then optimize that. So yeah. If we have customers, so basically if non-optimized stuff is good enough for customers, then great. If there's no customers that care about running stuff without Viridian, whatever, then that's great too. But if we have customers that are like, I can't use the Viridian extensions for whatever reason, but I want to pay you some money, then we'll do some work.
And it first needs to be correct.
Yes, it first needs to be
Yeah.
correct. It doesn't matter how fast or slow it is, you get it correct first. And
Yeah.
then you figure out what to optimize.
Yeah, and that itself is going to take a long time. So let's focus on that.
In our case, specifically for Zen Server, the two big things we want it for is for the CBAD workload, so virtualized desktops, and they care about WSL2, which is actually running real Hyper-V under it, and they also care about it for a thing called virtualization-based security, VBS, which is a number of technologies.
Which I briefly covered in the first talk. So I forgot to mention WSL, but I did mention VBS.
Yeah, so WSL2 is the other big thing that just uses Hyper-V under the hood these
It
days.
got deprecated. Application guard that got deprecated.
Application guard is just one of a small
I know.
number of things. The point is, we Zen Server care about making it do it on Windows, so one way or another we're going to be using that Viridian extension because
Hyper
Yeah.
uses it.
Well, it's available, and it'll make things a lot faster and a lot less work. Yeah.
it's available and it will make Windows go faster, so
Oh.
we will be doing it.
Alejandro?
So, yes, you said many features are exposed on MSRs. Do you on Ether, do you have, is that a reasonably small number of MSRs? Or,
It's 17 MSRs, pretty much packed full of bits.
are we talking reasonably data?
The MSRs themselves are read-only data. They describe what is permitted to read and write in various control fields.
I'm guessing we want to put that in the
Theoretically
policies soon.
read-only. Sorry?
I'm guessing we want to put that in the policies soon, so we migrate it.
Well, until you enable nested virt, it's not there at all. But
We're not passing garbage. Hopefully, we're passing zeros to those things.
and well, there's nothing to pass. So yes, it is all zeros.
Well, so I think he's asking, so if you read those MSRs in a guest with nested HVM disabled, what will you get?
You now get zeros back.
Okay.
So you remove default readability of MSRs. So
It's not zeros, it's a GP fault.
sorry, yes, it would be a GP fault.
Okay.
But
Okay.
yes,
Okay, fair enough. So it's not something that we have to care
we
in
did
terms of
used to
passing the right
host
data.
VMX MSRs into general HVM context because they said, yeah, everyone can read all MSRs.
You used to leak everything.
Yeah.
Used to leak everything.
Especially those MSRs, because they leak everything.
Okay, well, thank you, everyone. I mean, we can take this offline. So, right, thank you, everyone.